Okay, the next presentation this morning will highlight some of the key trends in today's design technology for overcoming engineering challenges, especially from Siemens PLM. Ladies and gentlemen, please put your hands together and welcome to the stage, Dan Staples.
Thanks so much. All right, thanks so much. And thanks for having me. So, as you said, my name's Dan Staples, and I work for Siemens. Guessing that most of you have heard of Siemens one way or another. If you've ridden on the underground, you've probably ridden on a Siemens train. Maybe at your doctor's visit or your dentist visit, you've seen Siemens equipment. Or even the lights in this auditorium probably have Siemens somewhere in the pathway to get this electricity to us. So we really cover all spectrums from automation, building technologies, mobility, healthcare, all covered by Siemens products. So we're widely known as excellence in world-class engineering. But we're also a world-class software engineering company as well. And so being both world-class software and world-class products, we feel like we're uniquely qualified to talk to you about the future of engineering. So what we see going on right now is actually the fourth industrial revolution. If we think back to the first industrial revolution, it was mechanization, water power, bringing in the early first revolution, steam power. And the second industrial revolution, which I think most of us call the industrial revolution, was really mass production, the assembly line, electrification, and so on. Of course, the third industrial revolution came from the 1970s onward, really with computerization, right? Computers and automation and the start of robotics and those kind of systems. But we're in the middle of what people often call now Industry 4.0, or the fourth industrial revolution, cyber-physical systems. The notion of having both a physical system, taking data from that, having machines that communicate with each other, being able to analyze that big data, and having a full digital twin that mirrors your engineering process. So it all starts with that digital twin, and I think the easiest way for us to conceive of that is initially the CAD model. The CAD model is the digital twin. But it's really more than that, because it's about not only the CAD model, but performance, simulation, manufacturing, the factory floor and all of your machines on the factory floor, and how are they communicating with each other, and what kind of data are they producing? Does one need to be serviced soon? And all that data comes back to us as part of the digital twin. And I can assure you that Siemens, with our breadth, can cover all those aspects, from initial concept design all the way through repair and optimization on the back end. Now, as I said, it starts with the CAD model, and I think many people think of Solid Edge, they think of a CAD system, and indeed, Solid Edge is a great CAD system. Solid Edge is, of course, the CAD system I'm most familiar with and responsible for R&D of. But you need to think of Solid Edge as more than a CAD system. It's really a portfolio of products, whether that is simulation to check product performance, whether it's manufacturing to produce the parts, the data management to keep it all flowing together, or apps like electrical wiring, piping, those kind of things. So think of Solid Edge as a portfolio of products. Now, you may also be familiar with Solid Edge just from your interaction with the world. So for example, nice Solid Edge customer, Voigt Hydro. They make hydroelectric power generation equipment, turbines, and so on. Use Solid Edge to design the biggest, most complicated projects on the planet, literally thousands of engineers running Solid Edge to design things like the Three Gorges Dam in China. Or perhaps you interacted with Solid Edge this morning in preparing your breakfast. So if you think of the brands like Tefal, Krups, Molenex, Rowenta, WMF, all these products are designed in Solid Edge. Or if you didn't make your own coffee, maybe you stopped at the Starbucks or the Costa Coffee or McDonald's, if you'll admit it. Solid Edge was used to design the machines that are used in those companies to produce the espresso. So I think you know Solid Edge from our customers. But not everybody uses Solid Edge. Some people use other products, I dare say. So I'd like to take a little bit of a survey in this room and just find out what other kind of products you're using. People who use SolidWorks or have used SolidWorks, can you raise your hand for just a second? I know people are shy, but that's good. What about Inventor? People who've used Inventor, that kind of thing. PTC, Creo line of products. NX, Onshape. Hey, there we go. Thank you, Onshape person. The funny thing about that is if you've used any of those products, you're actually one of our customers. You've actually used Siemens technology. So Siemens technology has provided the basis for all of the products you see on the screen here. So whether it's a geometric kernel of some sort, or it's a solver, either a 2D sketch solver or a 3D assembly solver, those are provided by Siemens and Siemens PLM. So I think of all of you as my customers in some way, and I want to talk to you about the technologies that we're going to continue to bring to market. Now, before we do that, I'd like to put a bow on a couple things from last year. The first was CAD and the cloud, and we said, yes, in the summer, we will deliver some CAD in the cloud, cloud-enabled solid edge, and in fact, we did so as we committed we would. But the key thing about it is how we approached that problem. We try to really look at our customers and what they want. So we tried to stick to the benefits and tenets of this, and in particular said, we want that CAD to be able to follow you wherever you go. So if you use your solid edge on device 1 or device 2 or device 3, you can have the one solid edge license and it can be used across those 3 devices. We want you to be able to share your CAD files easily, and so we don't have some special way to do that. It's something where we partner with people like Dropbox or OneDrive, Google Drive. You have the ability to collaborate across your teams very easily in a very comfortable way. And finally, and very importantly, CAD that is reliable. So we don't think it's acceptable if the internet goes down, the internet is slow or spotty. We don't think that's acceptable in terms of your CAD and engineering process. So in the case if the internet goes down, solid edge does not go down. And even though we say this never happens, it just so happens about 2 weeks ago, the internet went down for about 150 of the biggest companies in the world for about half a day. Took down a lot of engineering processes, but solid edge just kept on cranking. The other thing we talked about last year, and I think this is really important, is creativity and how great products are created by people who can think and be creative, but be able to change their mind. Part of the creative process is being able to change your mind, try different alternatives. And we talked about the fact that if you're using something that has a strict history tree, it's difficult for you to change your mind, which by definition means you're not going to create as innovative or creative a product. And so if we're recycling history-based technology in new media, like the cloud, we're really not solving engineering problems for you. And we think it should be done differently. So I used this slide last year of saying, well, what if you had this design on the left, big heavy plate design, and you thought, oh, I could do this differently. I could do this, and you've got this in your mind on the right. But you say, how am I going to get there? And you say, in a history-based system, start over is absolutely the answer. And I would start over if I was using a history-based system, for sure. But I said, you could do this in under 2 minutes to get from what's on the left to what's on the right in solid edge. And people said, well, I'd like to see that. So I brought that with me this year. I've got this sped up 2x, but this clock is real time. And you're going to see this magically transformed from the thing on the left to the thing on the right in under 2 minutes of wall clock time. And so you see that the rib has magically become the sidewalls. The sidewalls get closed up. And what I want you to be noticing here is just the flexibility. You would never undertake this in a history-based CAD system. So we need to round up a few things here. But basically, you're able to repurpose the geometry, and this is fundamentally important to the creative process. If you think you can improve your design, but all of a sudden your CAD system is constraining you from doing so, you're not going to get to the best design. Notice I'm not going in and out of profiles or sketches. I'm not going in and out of parts a lot. I'm able to sketch directly, have things region automatically, maybe round up a few corners here and there. And in a second, you're going to see us editing multiple parts at once. Again, not going in, rolling back the history tree, rolling forward the history tree, not any of that. So I need to adjust the stand as well. It's now round, and I'm going to make these 2 parts taller all at once. And here I am at 1:52, all done from what you saw on the left to what you saw on the right. So this is game-changing stuff, and I invite you to learn more about it. Okay, but advancement never rests. So there's been a lot of talk this morning about new technologies, and I want to talk to you about some very important new technologies, including one that hasn't been discussed at all yet this morning. So I want to cover 4 different things: generative design, additive manufacturing, reverse engineering, and the missing link, that one piece that ties all this together in a way that makes it uniquely useful. So let's start with generative design. And this term has been used a little this morning, but I want to talk a little bit more about it. So generative design, some people this morning have called it topology optimization. Sometimes it's called shape optimization. Sometimes it's called generative design. We think the term generative design is the most appropriate term because it is helping for the computer to generate the design for you. So whereas we might be working on a new electric bike and this might be our concept of how we want it to be. If we let the system do the engineering for us, we might end up with something very different. You define some constraints, where the wheel is going to attach. I need you to keep out of this area for the electric motor, and I need you to generate an optimized, stress-optimized design for me, and we might come up with something like this. So let's take a look very briefly at how that works. I've got this part that I want to work on, and it's very chunky, and so I want to remove some weight from this part. So I'm going to apply a load on the left. I'm going to apply a constraint on the right, and I'm going to ask for it to generate the generative design. And what you see is a highly optimized design where it's taken the stress into account to remove material and get us a much tighter design. So as you can see, it can actually generate some very, very beautiful parts. But one of the things that I find most interesting, we were working with some beta customers 2 weeks ago. And a lot of our beta customers were very industrial, machinery-oriented companies. And I was talking with one of them who actually they're the world's largest maker of gas compression, Ariel Corporation. And they're already working with this kind of technology saying, even though we're industrial, we make very big designs, very heavy castings. And if we could take a casting that weighs 50 or 100 pounds, we could take a quarter of the material out of that, to us, that's every fourth part is free. And I think that's an amazing way to think about this. So whereas we want to think about this often and we think, hey, this makes sense for aerospace engineering, but I don't do that. I do industrial machinery. Well, let me tell you, there's lots of money to be made in industrial machinery by lightweighting these parts and reducing your material costs. Now, something very important to point out, particularly from all the things you've seen this morning. I think if you've seen topology optimization, generative design, what you've generally seen is this software that runs for a little bit and it creates this really ugly model that has lots of lumps all over it and weird stuff. And then you personally, as the designer, have to go create a beautiful model using that as a visual guide. And that's all well and good, but that is not the state of the art. What you see on the screen here in front of you, these parts came directly out of the generative design system. There is no post-processing on them whatsoever. They come out that complete and beautiful and ready for production straight out of the system. The next area is additive manufacturing. As I think Brian was saying, you can't throw a rock without hitting an additive person here. One of the more interesting studies I've seen of late, or one of the news articles of late, this is from NASA. So this is a finger splint up in space. Really interesting application of this technology, and it's really like mass customization, but says, instead of having to ship all sorts of medical supplies up to space, custom fit for each astronaut, I'm just going to ship up a 3D printer. And I'm going to print things as needed. This is a great application of using additive manufacturing to do custom work. But if I was to look around at everything that's going on in additive and say the one or two things that's really super important in my mind, it's true additive manufacturing of real-world heavy-duty parts. So this happens to be a Siemens turbine blade, and this was produced with additive manufacturing. It uses some super advanced powdered nickel polycrystalline super alloy. Try to get all those words in there. And it actually produced this part, and it goes into production in some of the world's harshest environments, right? It's spinning at thousands of RPMs. It's got high temperatures. It's got cooling channels inside of it, things that can only be done with additive. This, I think, is where the real value in additive is going to be, is in these truly heavy-duty manufactured parts. But what if you don't personally own a nickel polycrystalline printer, let's just say? Then there are other ways to get this done, and it's really, I think, a kind of a democratization of additive manufacturing. So what you see on the left is a scale model of this designed in Solid Edge, and it was actually printed with a service called 3 Year Mind. This is a service that I think is very, very interesting. So if you think about all of you and when you travel, you probably use Kayak, Booking.com, something like that, to be able to aggregate all the different travel offerings and be able to figure out which one you're going to use. What we can do here is aggregate all the 3D printer services and figure out what one you're going to use based on lead time and cost. And so it looks something like this. I have my part here, came straight out of the Generative. And here I have all these different materials that I can choose from. These are from many, many different services. And in this case, I choose this polyamide. And it says it's going to be 3 to 6 days, and it's going to cost so much based on different people. And I actually choose amongst the suppliers and say, I want this supplier because he's the cheapest, or he's the fastest, or he's the cheapest and the fastest. And so you can see here I then get a report that says, hey, in 4 to 7 days you'll receive your part, it will cost you $28. So those of you who've been thinking, hey, I want to do something with additive, but I don't really want to go out and buy a machine at this point. I want to just start to get engaged with it. This is a great way to get engaged because you can get everything manufactured and all the different materials and just get it on your desk a few days later. Reverse engineering. This is a great example of reverse engineering. This is a replica car, a Shelby Cobra replica car, where they have the physical model but not the CAD model. And so with our partner, one of our partners here in the UK, Magenta PLM, they scan this data into the CAD system. So we scan in the Shelby Cobra body, and we can do many, many things once we've captured that electronically, right? We can, for example, create technical documentation of some sort. Or we can create a beautiful rendering. This particular rendering was made with Keyshot, in my opinion, the most awesome renderer in the world. Also happens to be built into Solid Edge and comes when Solid Edge ships Solid Edge Classic and above. So people can create these renderings very, very easily on their own. So that's very interesting. We have those 3 different technologies, but there's a problem here before us that nobody's really talked about. And that problem has to do with this. So if you will take a map here for a second, a key. Blue means mesh model. When I say mesh model, I mean points that have been connected into triangles that are connected together into a mesh. Okay, so that's the mesh model. On the right, we have the BREP model. The BREP model in orange is what all you folks who raised your hand and said, I use ProE, I use SolidWorks, something like that. The BREP model is a solid model, the regular solid model we all know and love. So they're 2 different things, the blue thing and the orange thing. And if we look at all the technologies that we've talked about, and many other folks on stage have talked about as well, generative design is a blue thing. It is a mesh model that it produces. So it may use voxels, for example, to do the underlying stress calculations, but in the end it creates a mesh model, connected triangles mesh. Additive manufacturing uses a mesh model. So additive manufacturing really started some 30+ years ago, believe it or not. And that technology, STL technology, is connected triangles. That's what's used to drive all these 3D printers. There's a new format called 3MF, but nonetheless, it uses a mesh model. And finally, reverse engineering. The scanners create a bunch of points. There's great algorithms to automatically turn those points into a triangulated mesh. That's what comes to us as the CAD system. But we have basically 3 types of mesh model that we have, and many people have been talking about this morning. And then there's the rest of us. We have our CAD system, our solid modeling CAD system. And we have lots of solid model CAD models, but we need to use those, and we need to use those in conjunction with these other technologies. So we would love for it to work like this. That I've got this beautiful generative design, and it just flows immediately into my design process, into my BREP model. I've got my reverse engineered scan. I got all those triangles back in some format, STL or OBJ or something. Flows into my design, flows right through to additive manufacturing after I make some modifications. Except that doesn't work that way at all, right? So we've got over here, we've got mesh coming from generative and reverse. Over here, we have mesh on the back end, and in the middle, we have this big island of BREP. These things are not interconnected in any way. And so it poses those questions, right? So generative design's great, and we said, with the state-of-the-art technology that we're describing here today, it can create a perfect, awesome generative design. But what if I need to make just a few little changes to that? Now what? And 3D scanning. It's a beautiful thing. I scanned it in, it triangulated it, except the dirty little secret is now I have to spend the next 3 days putting B-spline surfaces on it in order to use it in some functional way. And additive manufacturing. We all know and love it. It's capable of creating amazing things, but what about the designs to drive that? We have to connect all this together. So what if I could work directly with the mesh model that comes out of my generative design? What if I never had to spend days doing all that tracing of the B-splines, creating a bunch of NURBs in order to get it into my system? And what if I had an awesome ready-to-print model? Let's say I got an STL from somebody else, but I wanted to make some changes to it. What if I could add and subtract features to that without having to turn it into a BREP solid model? And that is, in fact, what I called the missing link. So there's a missing link to tie all these three technologies together and make it useful to you and your business. And that missing link is called convergent modeling. It's something we've introduced very, very recently that allows us to tie all that together. So let's take an example of how this might work, right? So in this case, we have our generative design, which created a mesh model, as you saw earlier. And we want to integrate it into the rest of our design. And to do so, it requires a few little changes. It needs a little counterboard hole because of the way it connects into the stand here. You can see this rod passes through it, so it needs some cutout for that penetration. So how does that work exactly? Now, I want to caution you, as you watch this movie, it's going to look like basic BREP solid modeling. And the fact is, I'm using all those kind of commands, but there are no BREP models at all as we watch this. So here I am, and I need a counterbore hole on this. I'm going to draw a sketch, create a region, just drag it, and create a counterbore hole that easily. I need to create a flat for a part number, so I'm just going to create a little protrusion. I'm going to create my little flat. I've got my part number text. I'm just going to drag it out and extrude it, and I've embossed my part number on the part. I need a cutout. It's in fact a parametric cutout. I want it to be so wide and so tall, and I want to cut that out through the part. And then I can take that part. Instead of putting my clunky thing in here, I'm going to put in my highly optimized part, and there you have it. So what we've done is to bring those two worlds together. The generative design, or the triangle-based stuff, whether it's generative, reverse engineering, or an STL file that you've gotten, completely integrated that into the workflow with the BREP model and your traditional modeling commands. And so when you watch that video, again, I think many of you would say, well, they're just doing solid modeling. What's so interesting about that? What's so interesting is that's doing it on a mesh model. There's no making of extra B-spline surface and all that work you have to go through. So if you're not familiar with the pain of turning mesh models into BREP models that exist today, I suggest you talk to people around the event who are. This is really revolutionary stuff that you're seeing here today. Okay, so wonderful technology. How do you actually get this wonderful technology? Couple points I want to make. The first is on the left here. So there are people at this conference today who will tell you, if you want to buy my software, you must buy subscription. We only offer it that way. That means when you stop paying, then you no longer have that software. Okay? We don't think that's right. We think that subscription should be a choice based on your capital structure. So if you are a larger company and you have a good amount of capital, and you want to buy a perpetual license, then buy a perpetual license. We offer perpetual licenses and will continue to offer perpetual licenses. If, however, you're a small business and you maybe are trying to conserve your capital and want subscription for that reason, then buy subscription. We offer either one, and we think you should decide that, not us. The same is true for licensing. There are other folks who will say if you want to use our software, you must use it in the cloud. We don't offer an on-premise kind of version. We, again, think you should be making that decision, not us. So if you want it node-locked, floating, cloud-based, it's really up to you to decide how you want that. Now, if we go to the right side of this chart, there's also a lot of free ways to get Solid Edge, right? So if you want to try Solid Edge, we offer a free trial. It's a very generous period where you have an opportunity to look at the technology and say, hey, I understand now why Solid Edge is better and different than these other offerings that I've seen. So free. Let me move to this side of the stage so you can see this. So if you go to Siemens.com PLM, try Solid Edge. You can get your free trial of Solid Edge. We find many, many people who try Solid Edge buy it in the end, either subscription or perpetual. Another more recent program is free for startups. And I know this type of event actually attracts many startups. And so I would like to tell you, and I will tell you, that Solid Edge is free for startups. So if you're a legitimate company, a legitimate startup company, you can get Solid Edge absolutely for free. There's an application process, but you can get it and start using it right away. Here's a great example of free for startups. So this is a customer of Solid Edge called Skybridge. And it's really interesting, too, because this is using all sorts of new technologies, too, like Internet of Things and big data and so on. So they build drones. This is a big drone. We're used to these little drones. This is like a big military-sized drone, a couple meters in each direction. But it's not for military purposes. It flies over crops, gathers information like, for example, the moisture content in the crops. And then it feeds that into big data analysis and provides farmers with information about how to do their crops better. And so this is a great place where they have taken advantage of Solid Edge on subscription and, in fact, the free startup program to be able to enable this kind of technology. We'd love to enable your company as well. And then finally, free for students. So free for students, Solid Edge student, Solid-Edge-student. Now, we are free for every student. This is a big distinction. This is not free for universities. Of course, it is free for universities, but it's also free for high schoolers, people who are in middle school, primary school. We actually provide Solid Edge for free for any student because we believe that they should all have access to this technology. But not only do we provide it as software, we also provide a program. So we've been investing for some period of time now in a program called Green Power. Green Power is the opportunity for students to design and build an electric car, but not only that, then race that electric car. This shows it's got high gravity. Students want to do this, and it really changes the lives of students who get engaged in engineering. And as we talked about a couple of years ago, there's a gap in engineering that we need to fill by bringing more students into the engineering profession. The particular gentleman you see in the car here is David Cullimore. Those of you who were here 2 years ago know that he spoke on stage with me because he'd won the last 2 international finals of Green Power with his car Jet, designed in Solid Edge. Well, he's continued to progress beyond that. Of course, he won last year also, and he continues to do great things. So the story doesn't end there. So I think it was actually when David spoke that he had just gotten a placement at Red Bull, thanks to the Green Power program and his investment in it. And so he had a placement at Red Bull, and we worked on that team as part of his education undergraduate. And since graduating, he's now got a placement that allows him to work on Aston Martin cars at ProDrive. And so this is a progression from student in their garage to real internship or placement at Red Bull to working at ProDrive full-time on Aston Martin vehicles. So we're really talking about preparing that next generation of engineers. So the final thought I want to leave you with is just about Siemens as both a world-class producer of physical objects, but also a world-class producer of software. And we think we're in a unique position to look at the world and what's going on, and we see this change going on, the Industry 4.0 change. We believe these technologies that you're seeing today and are talked a lot about, generative design, there's a new state-of-the-art where you don't have to post-process it at all. Additive continues to be very important, and particularly additive manufacturing, very important, reverse engineering. But most importantly, convergent modeling is the tool, the glue that allows you to pull all these things together and suddenly make them all relevant and a part of your design process. Now, the final thing I'd like to leave you with is just opportunities to engage with us further. So I'd personally love to talk to any one of you. We have 2 things going on here at the show that I would invite you to visit. The first is because we believe so strongly in Green Power, we've donated our booth to Green Power. And in fact, you'll find David is there with his Jet 2, his 2nd generation Jet car, and there to talk to you about the Green Power program. The other is virtual reality. So there's actually a cooperation between Siemens and Dell. If you go down into the studio, which is on the left as you go out, there is in fact a studio there where you can try out virtual reality products. You can also test drive the Solid Edge product. It's something you have to sign up for, and there's ones going on right now, and again at 1:30 and 2:30, so take advantage of that opportunity. I'd also like to give a quick shout out to Develop3D. They recently did an entire edition on virtual reality, lots of good stuff in there, and I'd suggest you take a look at it. Thanks very much.